Hi, so welcome back. If you've just watched the video on the differential voltage and current measuring, you'll know exactly what I'm going to be talking about now, and that is integration. The way that I want to move forward with the power supply project, keeping things simple, is I have a differential circuit with a summing junction on the output of that from the voltage reference set points that will basically give us a 0 volts output relative to the analog supplies of the op amp, where the set point through a potentiometer or a digital to analog converter and the measured current or voltage of the actual power supply, where they're equal, the output will be 0, and where they start to deviate, either plus or minus, the output of the integrator will either ramp up or ramp down, and we'll use this to drive the MOSFET. Obviously, when it starts to ramp down, which implies that we don't, that we've exceeded our set points, then that'll turn the MOSFET off and reduce either the current or the voltage or both as appropriate. Now, for an integrator to work properly, obviously, it relies on the fact that you have a nominal 0 volts on the input, at least in the one we're going to use, and that it will ramp up over time as long as there's a difference between the inputs of the differential of the comparator for the integrator. Now, these things are not perfect. There's always slight voltage offsets and things like that, but either way, they still work very well, and I think that they'll be very useful for the power supply to control the output. And this is actually the same idea as Agilent and other major power supply manufacturers use to control their power supply. So it's not that I came up with this necessarily on my own. I won't pretend that I did, but I did get inspiration from looking at old circuit diagrams for power supplies that are probably over 30 years old and how they did it there. And it actually made sense once you start looking at all the different things about maybe wanting to have your control circuitry sitting on the positive rail, wanting to have high side current sensing, not wanting to have operational amplifiers that have to have massive big supply rails on them. Once you start adding all of those factors together, using an integrator to control the MOSFETs and things like that also makes sense, because it gives you the ability to respond appropriately at different speeds depending on the amount of deviation from your set point that the outputs are. But also, at the other end of the scheme, if you've got a very, very tiny offset, then the circuit will still slowly compensate for that and ramp the output until it gets there. There are nuances with it, though, of course, where you might get some oscillations and things because of the fact that it's never going to be exactly balanced on the inputs and the outputs of an op amp. That's just the nature of what they are. But obviously, the closer they are to 0, then the integration period is going to be massively reduced. So it's really going to be a very, very stable circuit, and I think will serve us very well. So anyway, let's go and have a look at the circuits I've come up with, and we'll move forward from there. So here's the circuit I came up with for the integrators, or that I'm going to use for mine. I've got a voltage integrator, so that if the output goes either way, the integrator is going to ramp up or down depending on the polarity of the input to the op amp. And the time constant is set by this 10 nanofarad capacitor in the feedback loop and the 100K going to ground. For the current integrator, I've got a slightly different set of parameters. I've got a smaller capacitor, and I've got a which is only about half the size of the voltage one, and I've got a 22K, which is about a fifth of the size. So what do we expect to see on this integrator once we start using it? Well, if we take the op amp, and we've got the positive input and the negative input, and what we're going to do is feed in here a step input representing a change in our sensed value. And what we have coming out, of course, in the feedback loop is we have our capacitor going to the negative input and a resistor to ground. All right. What's going to happen is we have this step input here, which is going to raise this, which effectively makes it positive to this. This output is going to raise, but because we have a virtual ground here, whatever this is, this needs to be the same as this, then you've got effectively a constant voltage across this capacitor, resistor, which results in a constant current, which means we end up with a linear change in the output. So let's just assume that this was all in a steady state with 0. The minute we hit this positive rise on the input, what we should see is a ramp going up on the output of the op-amp. And the longer this stays positive, obviously the output is going to rise until it gets to the supply rail or close to the supply rail of the op-amps, in which case at that point it will saturate. Now obviously if the output the input goes negative, so it's been sitting at 0 and maybe now it goes negative, then the output is actually going to do the same thing but in the negative direction. All right, until it gets to either the supply rail or until the input now starts to come back. Now this obviously is going to be controlling our MOSFET. All right, so it's going to be having a feedback loop that's going to go through the MOSFET to the output stage, through the current sense or the voltage sense, and back into this input. Now there's a time constant to this, of course, so the more rapidly the input changes, the more that this capacitor is going to stay in effectively, for an instantaneous change, this capacitor is going to be effectively a short circuit between here, which means it's going to have unity gain. All right, so a few millivolts change here, and so like a little spike is going to have no effect whatsoever, or virtually no effect here. But any output that stays high for a period of time, this obviously as the capacitor charges up, then due to this time constant, the output is going to slowly raise. But as long as this input is on average staying at 0, then the output on average is going to stay at 0 as well. And you might end up with a little bit potentially of an oscillation, where if this is on the input, if this is basically just sitting here due to the load doing something like that, just a gentle oscillation, then the output is going to be sitting just doing a gentle ramp up and down as well to go with it. Now obviously one of the nice things about this, we're talking about transient response time and things like that for our circuits, is if let me just erase this a second. If we have a small change in the input like that, then you're only going to get a very long drawn out change on the output. It's going to take quite a while for that output to ramp up in order to balance this circuit going right through, because the voltage here, remember this is a virtual 0 volts, a virtual ground compared to this. It wants to keep them the same. So if you've only got say 10 millivolts offset here, then you've only got 10 millivolts across this resistor, right? Which is going to be, let's just say that's 10K. You got 10 millivolts. That's only going to be like 10 microamps or something. Very small current flowing through that resistor, which means it's going to take a long time to basically charge this capacitor up to the supply rail. But if this input is actually, we just pick a different color here. If this input is a large change relative to the 0 volts, so say that's this one was like 10 millivolts, maybe this one is 10 volt change or something like that instead, then because of that, this is now 10 volts across 10K. That's going to be a lot more current, in which case the rise time of this slope and the charge time of this capacitor is going to be significantly more. All right, because that input step is more. Now what this gives us as an additional benefit of, not only is it giving us this little gentle correction when we have a very slight offset in our set point and output, but it's going to give us a much faster response to large transient load changes on our actual load of the power supply. Because if you suddenly go from say 100 milliamps to a 5 amp load, normally that's going to dip your power supply quite low quite quickly. But because it suddenly measures this large offset on the input to this, the integration is going to be much steeper because of that, and it's going to recover from it very quickly. So what do we actually want to see in this? What we want to see is something, in the measure of microseconds, maybe 100, 200 microsecond response time for a large step change on the input. But if you've got a small step change on the input, you could probably allow it to correct itself over the period of tens of milliseconds even, and that would be probably more than adequate for a power supply. And you don't want it to be responding to small changes very rapidly, because what will happen is it's going to break into oscillation or something like that. So by having this effectively like a dynamic feedback based on the effectively it's a proportional feedback, I guess, even though it's using an integrator, based on the size of the change, the rate of correction is going to be much faster. We've got this nice characteristic of the power supply, and this is something that, as I said, Agilent and other power supply vendors have been doing for years. So it's not surprising that we've ended up getting through all of our design and talks and theory to something that's basically the same idea. All right, so that's what we want to have a look at. Now let's go to the actual breadboard and see if this works in theory. Sorry, that's the theory. Let's see if it works in practice. Okay, for the moment, just because I want to just show the integrator, what I've used is a 2 op-amp version of the TLE 2144. I'm using a TLE 2142 chip here, which is basically it's the exact same op-amps. It's just in a 2-chip package. I don't want to disturb our other one, and it's all crowded in there. So I want to show you the theory of this working before we actually hook it in, and then what I'll do is I'll rewire the other quad op-amp, and we'll have this circuitry as part of it. So what I've got here is I've got my oscilloscope probes set, measuring the, just zoom out a little bit there so we can see. I've got my oscilloscope probes. This one here is connected to channel 1 of my oscilloscope. It's actually measuring the input from my Agilent 33622A function generator. And I'm going to set that for a square wave of around about 10 Hertz or something like that. We may adjust the frequency just to play around with things. And I'm going to start off with a 1 volt RMS, so it's a half volt positive and negative, centered around 0 with a 50% duty cycle signal feeding into the op-amp. I've got a 100K and a 22K as per our circuit. For the current integrator, I have a 4.7 nanofarad feedback capacitor and a 22K going to ground. And the previous diagram that I showed, I think I had the wrong value here. It was up at around 2.2 microfarads or something like that, which of course is totally wrong and way too big. So this is more in line with the value that I want to be using, is the 4.7 nanofarads. And why is it 4.7 nanofarads? Well, because that's what I happen to have in my parts bucket too. It's a fairly standard jelly bean capacitor, so that's what I'm going to use here. The 22K is a standard cap, and then on the voltage integrator, what I'm going to use here is a one that's about 10 nanofarads, so it's about twice the size, and I've also got a 5 times the size resistor in here, the 100K. So let's go and hook those up, and we'll see what happens. Now, I expect to see the voltage integrator is going to be running at a slower integration time than the current one, because the current one is 4.7 and 22. The other one, so the capacitor is half the size of the voltage one, which would typically double the ramp time, but my resistor is a 1/5 of the size, which means that, once you've got all that compensated for, there's probably going to be about a 2 times difference or something without doing the actual math between the two circuits. So let's see what we get. All right, I'm going to rearrange this and show you on the oscilloscope, because there's nothing really much to look at down here at the moment, because I'm feeding the signals in, and you're not going to see anything happen down here. So let me rearrange things and we'll go from there. Okay, so here's the oscilloscope setup. I've got it set to a time base of 20 milliseconds. I have an input frequency of 10 Hertz, as I said before, with a 1 volt RMS input going into it. And it has a 50% duty cycle. The yellow waveform is the input signal. So right now it's set to 500 millivolts. Let me just reduce it down to make it easier. So there you go. So we've got the yellow signal traced out, nice square wave from my signal generator. And the blue signal is the current integrator, which has got the 22K and the 4.7 nanofarad capacitor on it. The purple trace is the voltage integrator with the 10 nanofarad and 100K resistor on it. As you can see, the slope is less on the voltage integrator, which is what we expected because of the changes in value. So what I'm going to do is I'm going to expand out the trace a little bit. So what we've got now is, as you can see here, with this 1 volt input, the integrator is basically, there's a little bit of a step on the very bottom and the very top here for some reason, but I'm not sure what that is. It's probably because it's sitting on the rail, and it's probably as it starts to come down, it's just jumping off the rail and then starting to integrate. So because that's probably what it is. There's a saturation point here where it can't change from the rail until the input has come to a certain extent. So anyway, here's the integration time from here to here. This is up to the positive rail, and this is obviously the negative rail. 0 volts is basically sitting here, and we've got 5 volts per division. So it's 5, 10, there's the 12 volts, and obviously 5, 10, and there's the 12 volts. So now you can see here, we've got 4 milliseconds per division. This is with a 1 volt change on the input. So we've got, from the time it changes, we've got basically 4, 5, 6 milliseconds roughly, maybe about 5 milliseconds from a 1 volt input, which represents, if that was current, that would represent potentially a 1 amp step change in the current load of the power supply. If it was the voltage, then it's probably representing 30 divided by 5, about 6 volts change in the output voltage, where it's taking about 4, 5, 6 milliseconds to recover. Now obviously if that's too slow, we can improve that by putting either a smaller capacitor in there or a smaller resistor to speed up the discharge time. So in order to speed that up, if we need to, and we'll find out once we get the actual power supply and do some real testing, we could play with the values of the capacitors and the resistors to adjust the tuning. On the voltage side of things, of course, it's taking a little longer to compensate. So we've got about a 6 volt change, and it's taking 4, 8, 12 milliseconds to correct for the voltage. Now, in the circuits that I saw from Agilent, they had about, let me just see if I can quickly find out. They were using a 6.8 microfarad capacitor on the voltage integrator, whereas we have the, I forgot what I put there now. We have a 22K, sorry, we have a 100K and a 4.7 microfarad. So we actually have potentially a slightly faster response time than what the Agilent would have had if they would in the system that they seem to be doing. And for the current side of things, what the Agilent systems have, or at least the ones I looked at, was a 2.2 microfarad and a 22K. So I've got a 22K and a 4.7. So for a current difference, I'm probably about half the speed. So I really should probably increase that. But we'll see what it's like once we actually get it hooked up with the system, because I don't know what the characteristics are yet, and it would be nice to see. The other way I could, of course, improve that is to reduce the 22K down to a 10K. On the voltage one, what did I say it was? Oh yeah, 6.8, and I've got a 10. So my voltage one would be a little bit slower as well. They just happen to be the values of the components that I had to play with. So, you know, you got to work with what's in your parts bucket when you're prototyping things on a breadboard, and that's what we're doing right now. So anyway, that's with a 1 volt peak to peak, 1 volt RMS step change. So what I'm going to do is I'm going to reduce the 1 volt change down to something like, I don't know, 100 millivolts or something, and we'll see what we get. All right, so that's 100 millivolts peak to peak now. And what we've got is basically the, one of them is, because remember I said that the integration is going to be very, very slow for this. So it's not actually allowing the voltage integrator to even really start notably coming off the bottom of its scale. All right, so you can see the current integrator is sitting on the bottom rail. There's probably a little bit of an offset. Either the power supply is not exactly plus or minus 12, or the, well, the op amps are never always, because they were bouncing off the rails, they're never always exactly balanced anyway. Sometimes they'll go to 0, but not to full plus rail. And slight differences, plus input bias offsets and things like that. I'm not surprised it's not quite perfect. So I'm just trying to figure out why one of the channels of the op amp is not switching compared to the other one. As you can see from the waveform here, the voltage integrator is not actually rising at all. the offset of the difference between the, by the way, the rising and falling edge of the current one is not because of a fault with the op amp, but it is. It's got a slight bias, and if I actually tweak the offset on the input to the op amp, you can see that I can actually shift the slope. So I've just raised it slightly, and you can see there that the rise and fall times are now basically going equal to high and low. Now this goes back to what I was saying before about various things not necessarily being balanced. I mean, number one, I've got it on a breadboard, which has got a lot of noise on it, and potentially the current loops for the power supply and things are not perfect. The power supply itself may not be balanced, and then, you know, I'm using 5% tolerant components, so there's a few things that could be causing a slight offset, but it didn't take much there to get that back into balance. But at the end of the day, it's not really relevant for what we're doing, so I'm going to put that back to 0 millivolts. And the only thing I can think of right now is that I've been playing with the capacitors a bit, and they seem to be fine. But my resistors, I've got a 22K feeding the to ground for the current side, but I've got 100K feeding to ground on the voltage side. And if you remember what I said, that we need to, I've put slightly higher values in there compared to what the circuit references that I had seen, because they're the only values that I have. But I've got a 22K here, and I'm going to just pull out the 100K for a moment on the voltage side, and I'm going to replace it. So it's going to probably do some weird things for a moment. Nope, didn't change, but I mean, right now there's no feedback. There's no capacitor resistor to ground. So I'm just going to put in the 22K now instead of the 100K there. Let's see what that does. Oh, there you go. So I've still got the 10 nanofarad versus 47 nanofarad capacitors in, but now, as you can see there quite clearly, the voltage integrator is now working just fine. And if I just adjust the offset volts a little bit, I'll probably get them to even be reasonably symmetrical. Yeah. Now you can clearly see there that the voltage integrator is still about half the speed of the current integrator. So I'm just going to change the frequency to 2 Hertz just so we can get a bit better signal on the oscilloscope. Hopefully it's not too short. There we go. So now I can increase the time. Alright, so we've just captured the waveform there. If I just expand this out now using the zoom feature of the oscilloscope, we'll be able to have a closer look at the waveform on both the rising and the falling edge. So here's the rising edge, and you can see from the step input, if I line that up actually with a marker, it'll be easier to measure. Okay, close enough. So from this stepping up, the integrator here starts to integrate for the current and the voltage, and we've got 20 milliseconds per division. Now remember, we're only doing an input change of 100 millivolts here, so it's very, very little. So we're taking 20, 40, 50 milliseconds to rise for the current to compensate, and we're taking 20, 40, 60, 80, 100 milliseconds. So that is pretty much twice the time. We've got 100 millisecond response time on the voltage integrator. Now that's, as I said, with a very, very small change in the sensed feedback. So that's actually pretty good. You probably wouldn't want that to go too fast. As I said, you'd end up breaking into oscillation or something if it was too quick. So let's increase the amplitude. Let's make it like let's go back to 1 volt on the amplitude peak to peak. So remember, that's 50 milliseconds and 100 milliseconds. So we're going to go 1 volt peak to peak now. Instead, let's just run that recapture. So this is now speeded up quite considerably. All right, I'm going to just increase the time base a little bit, and let's just stop that. And now we'll measure that rise time and see what the difference is. My current, of course, is off the scale here. Sorry, my input trigger is off the scale, so that's back in. You can see where the start is right here, and this is going from the negative to the positive rails and hitting against them. So let's zoom in now on this and see what we have for a rise time now. Remember, it was 50 and 100 before. So let's just line that up with the marker. Okay, So now we're running at 2 milliseconds per division. So we've got 2, 4, 5. Now basically going from 100 millivolts to 1 volt, we've gone from a 50 millisecond rail-to-rail transition. Now we're doing the whole sweep in 5 milliseconds. So you can see that if we had a 1 volt input change, which represents about 20% change in your load or 20% change in your voltage for whatever reason, then this would recover from that effectively in about 5 milliseconds. And the voltage would recover in about, well, 2, 4, 6, 8, 10 milliseconds, 10 to 12 milliseconds. Sorry, yes, 2, 4, 6, 8, 10, about 11 milliseconds. So that's literally 10 times faster than what we had before. Now if I go up, remember when we were looking at the two differential amplifiers, they were basically running from about 0 to minus 5 volts on their output, minus 6 volts. So let's put a 5 volt peak to peak and see how quickly that responds. So basically this will be equivalent to turning your load on, or turning the output on the power supply, or having a load variance that's going to go from maybe a standby state to a full load state very, very quickly. Now remember, I'm changing these inputs on a very, very fast edge from my from my waveform generator as well. So let's now change this to 5 volts peak to peak. All right. Now this is peak to peak too. It's not peak, so it's actually only a 2.5 volt transition on here. So let's now capture that waveform, and you can see there now it's even faster than what we had before by well, we had 5 milliseconds and 11 milliseconds. Now we're actually running. All right, so now we're running, here's the transition state. So we've now got 400 microseconds, so 0.4, 0.8, 1.2, so 0.4, 0.8. So it's about 900 microseconds now that we've recovered on the current change, and we've got about 4, 8, 12, 16, 1.8 milliseconds recovery time on our voltage range. And that's only 5 volts peak to peak. So that's going from being above the range that we want to being below the range that we want. So if we can increase that to 10 volts peak to peak now, I'm going to go to 10 volts on the output of the waveform generator. Okay, so that's now set 10 volts, and let's just capture that again. And now you can see again this has significantly reduced now. We've only got 400 microseconds response time for the current, and we've got about 800 or 900 microseconds response time for the voltage. And that's going rail to rail. And this is only a 2 hertz signal. Obviously, if I, reducing the transition time any slower wouldn't make any difference to this integration, because it's going to hit the rails within a couple of, a few hundred microseconds. But what I can do is change the input shape. So right now we're running with a square wave. Okay, so that's where we were at before with a 10 volt peak to peak signal. So there's our 5, 10 volt peak to peak switching. So we're at negative rail here. We're going all the way back up to the positive rail. And you can see that there is a bit of a step here, a sudden jump from the ground rail when it comes up. And I'm sure if we look at the other end of this signal, we'll see the same thing there. I'm not quite sure what that effect is, but normally you would not be banging this on rail to rail anyway. You would normally be sitting just around the central point, which is the operating range of the op amp. So this is the last one I'm doing. It's a 20 volt peak to peak. Now remember, I'm running a 12 volt plus or minus supply here, so I'm just sitting the input just below the supply rails of the op amp. I've still got this step here, which I think is something to do with the very rapid rise time I've got on my input signal with the op amps coming back into play. And then you've got this integration. So if you still count the integration, basically we've got 100 microseconds. So we've got about 150 microseconds on the current, and about 300 and a bit on the voltage. So as you can see there, the faster the input changes and the larger the range of the input change, the quicker the response time of the integrator is going to be to try and correct for that. So what I'm going to do is I'm just going to give it a different signal. I'm going to reduce down the noise. I'm going to reduce the signal down to maybe, you know, something more realistic, say maybe a 1 volt peak to peak, or let's go 2 volts peak to peak, so that represents 1 volt on the input. So let's just run this now a little bit quicker, and let's change the scale so that we can see it all. Alright, so that's running with a on there, that's got a 1 volt peak to peak, 2 hertz signal. Now I'm going to change the waveform. I'm basically going to say I'm going to generate just noise now on this so that we can see what the integrators will do. Now right now, let's just change the frequency of this noise, because right now it's sitting with a 100 kilohertz of noise. I'm going to change the bandwidth of the noise down to maybe let's just say 1 kilohertz, and the offset, so you can see here it's got 1 kilohertz of noise, and those the integrators are going a little bit crazy here. Trying to compensate for that. I think that the noise is not quite sitting on 0. So it's basically driving them down. Let me see if I can change the noise amplitude down to 1 volt peak to peak. Because what we really want to do is have this sitting at around 0. We really don't want these comparators to be sitting on one rail. There is an inherent issue with with integrators, though, that they can drift to one of the rails if you don't provide a feedback path on the integrator. You know, you would normally put something like a 10 times resistor across the capacitor, which limits the bandwidth gain so that you don't get a bias voltage inherent on the capacitors. Now we can have a look at that to see what's happening here, because obviously with this noise, it's only set 1 volt peak to peak. It's ground reference, which means that, you know, on average with the noise, it should not be going above. It shouldn't be driving it to one rail. I mean, if I just play with the offset a little bit, see if I can bring it up. Yeah, it seems to be drifting a little bit. So what I'm going to try and do is, one of the channels, I'm actually just going to put a resistor across the voltage capacitor right now and see if that makes any significant difference. Alright, so I put 100K across the capacitor that is part of the voltage integrator, and that's obviously, as you can see there, that's slammed it right back into the center, which is exactly where I would want it to be. Now, in order to make sure that's working properly, let's go back to having a square wave with a 1 volt peak to peak, and you can see there that it actually is still functioning, but of course, because there's now a limited gain on it, it's not it's not going rail to rail, which is not really what we want. And you know, like I said, you want to have at least a 10 times value. So I'm just going to dig out maybe a 1 mega ohm resistor instead of 100K and put that in the place of the 100K and see if that makes it better. Well, I guess the theory is correct. I'm not sure how Agilent managed to avoid this, but I've just put a 1 mega ohm resistor in parallel with the capacitors on both sides, and that's now basically pulled the voltages that I'm seeing on the output of the integrators up to, well, roughly, I'll say roughly 0 volts. I mean, they're still slightly off. If I play with the offset voltage just very slightly, that'll probably correct it. That's about 10 millivolts of offset on that noise, and that looks like it's sitting it right there, right on the output. So, you know, that's doing quite good, because that's 1 volt of noise that's being introduced, and obviously the outputs are compensating for it. And that would be a lot of noise that is on the output of the power supply being generated by something, if that was really the case of what was happening. So, that actually, what's interesting there, though, is I replaced one of the 100Ks with a 22K earlier because it was hitting the bottom rail, and I'm just wondering whether the effect of that was because of this biasing of the capacitors towards a rail, and you know, because of charging up the cap, and not actually an issue with the op amp or anything. So let me just put the 100K back in on the voltage one, and let's see if it fixes it. Okay, I've now put the 100K back in on the voltage integrator, and it's still sitting there nicely. Now I've still got the 1 volt peak to peak. So let me just go back to the same signal that we were using before, which was a about 100 millivolts amplitude peak to peak signal. So you can see now that the gain of the voltage has now changed because we've put in the 1 megohm across the capacitor, and we've got a 100K input now. So obviously that's changing the dynamics a little bit. But let's reduce this amplitude down back now to 100 millivolts where it was failing before, and see if it actually continues to work. We'll probably have to adjust the triggering a little bit just to make sure it's going to work here. Alright, so I've got a 60 millivolt peak to peak signal going in here right now, and what you can see is that the integrators are no longer, because I'm probably so close to the noise floor and things like that now, the integrators are not going positive or negative, and because of the 1 meg feedback resistors that are now across those capacitors, the gain is not sufficient to continue driving up enough. So I'm going to quickly change those 1 megs for 10 megs and see if that makes a difference. So you have to remember here, we're not trying to interfere with the basic nature of the integrator, which really ideally has an infinite gain. What we're trying to do is limit the electrical properties of the offset going too high. So I've just pulled out the voltage 1 meg right now, and as you can see, that's basically just dropped back down to the negative rail. I'm just about to plug in the 10 meg across the cap instead of the 1 meg, and let's see if that brings it back but allows the gain to be there. So that really didn't fix it. My fingers, I think it makes it very susceptible to noise, as you can see there, which is not good. Yeah, but I think what might work better there then is to have the 1 meg in play, but put back the 22K on the input instead of the 100K. So I'm just going to do that now and see what we get, because I think that might be enough to allow this to work properly. So I'm just putting the 22K back in now. There. So that's now a 22K with the 1 megohm resistor, and it's now sitting back up. It's not going above the positive rail. That's probably because, again, with we're talking now, we're in the region where offsets make a difference. So I've just added 7 millivolts offset to the input signal, and you can see here that it actually does make a difference. I can just crank that up and adjust the average of the integrator outputs. So I think I'm not, I can play around with this more, but really just to have you hanging around while I do that is not worthwhile. Even there, I've got the 1 megohms across, so I think I'm going to keep those in the design. I mean, we're talking about 60 millivolts peak to peak, which is only 30 millivolts peak. So we're talking about the response to a very, very small deviation on the input signal and the limits of the gain of the amplifier. Now that may be, I don't know, too much. I guess the other option, of course, is to reduce the 22Ks down to something like a 10K. So I think what I might do is just as a last-ditched effort, the capacitors I could probably improve by putting better quality ones in. But let me just try a couple of 10Ks instead of the 22Ks, and that'll be our last test to see if this thing can be improved a bit further for the integrators. Alright, so what I've now got is I've got 10K resistors on the on the integrators down to ground for each of their respective capacitors, and obviously that's improved the gain because the feedback with those 1 megs is definitely reducing the gain there. I mean, perhaps having something in between the 10 and the 1s might be enough to fix it, but I think that it's just a case of playing around with these values a little bit more to try and figure out what's going to work for us. So we'll have to come back to that. All right, just been playing around a little bit, and what I've done is I've actually simply removed the 1 megs back out of the circuit. I've right now got a 60 millivolts input signal, and you can see that the integration here is still a little skewy to one side because of offsets and things. But like I said, it's breadboard, probably slightly unbalanced power supply rails and things like that. But nevertheless, it seems to be still managing to get from rail to rail. If I increase the amplitude back to, say, 100 millivolts, I bet you it's going to square it up nicely. Yep. All right, it's just in that lower end when I get down to, I'm down to 50 millivolts there now. It's still working. It's just starting to go probably into, that's just killed it when I went to 40. So the outputs are not responding at that point. They're just sitting on the negative rail now. 50 millivolts peak to peak on the input is enough to start causing integration to occur on that. Now, I don't know if I've got any other op amps. I might have. So the last thing I'm just going to quickly do is see if I have another op amp of a different kind, and we'll drop that in and see how well it performs, if it's anything significantly different. Be right back. Okay, so I found a few. I've got 3 choices. I've got they're all Texas Instruments. I've got a TLC 272, a TLC 277, and I have a TL082. They're all the same pin out. They're all capable of working to the same range, and the main differences are the TL082 has got a JFET input, so it's extremely low input bias currents or anything like that. So very 30 picoamps and low input offset current of about 5 picoamps. Harmonic distortion, etc., are all extremely low. So this thing is used for usually for higher end devices and stuff like that. And then the other 2 I've got here, they're both on the same data sheet. They're just, the differences are the offsets basically, is the TLC 272 and the TLC 277. And the 277 actually only has about 500 microvolts of offset noise on the TLC, right, max at 25 degrees C, as opposed to, I think, a millivolt or 2 on the TL272. So I think the 2 that we're going to try here, just to see if they make any difference, will be the TL277 and the TL082. The other one is just a lower spec version of the 277, so we'll just skip that one. So let's go back here and we'll switch them out and we'll see how we do. So I'm going to leave the inputs right now exactly as they are so that we can do a side-by-side comparison. This signal that we're looking at right now is the current op amp, which is the TLE 272. 2142, sorry, it's the TLE 2142, which is the one we're currently using, and I don't have the input specs of that one at the moment, but let me just power this off, and I'll just switch out the op amp and we'll see whether it makes any difference. So the first one we'll put in is a TL082. Okay, so that's the TL082, that's the JFET input operational amplifier, and whilst it has certainly basically kind of zeroed itself across the, centered itself across the zero line, it is certainly doing some weird behaviors there. So not too impressed with that one. So let's unplug that and we'll try the TLC277. And as you can see from the smoke, I just managed to fry the TLC277. As soon as I powered it up, it basically went up in a poof of smoke. So probably doesn't like the voltage. No, looking at the spec sheet, I kind of boo-booed there. It does not. It's actually only a 3 to 16 volt or 4 to 16 volt. It's actually not split rail. So oops, I guess I should read the spec sheets a little closer. So I actually don't have an op amp that's going to perform better than the ones we have already. I guess moving on, so I'll either have to figure out how to get the TL082 to work, or just go back to the op amp we had before. Okay, so I'm back with the TL082, and what I've done is I've put back the 100K and 22K resistors on the capacitors to ground, and this one actually is behaving quite nicely with it right down to about 50 or 60 millivolts, which is still better than the TLE2142 was doing. So you know, we've got an option now of using one or the other. The characteristics are slightly different, and you still get a little bit of the offsets and everything else. This may work much better if I actually build it up onto an actual circuit board, a vero board or prototyping board or something, rather than the breadboard, because it'll eliminate a lot of the ground noise and other offsets that you quite often get with working on breadboards like this. But what you're looking at right now on the oscilloscope screen is it's a 200 millivolt input peak to peak, which means it's 100 millivolts either side, right? So we're at 50 millivolts per division. The outputs here, which are set to 5 volts per division, you can see that they're quite nicely sweeping, and they are about even right now too, which is nice because I have no offset. So this is actually keeping the charge and discharge cycles of the cap a little bit more linear in both directions. I think it's still a little faster on the charge side than the discharge side, but it's definitely working. So if I reduce the output now to the input to 100 millivolts swing, you can see here that because the slope time is so much slower, it really isn't able to get off to the other extreme before it starts to come back up again. So what I'm going to do is I'm going to reduce the frequency down to 1 hertz and see if that actually helps. So there, you can see that it actually does. Now it's actually going still from rail to rail. Because I'm working with such a small input signal now, it's only a 50 millivolts change on the input of the op amp. Obviously the current now that is charging and discharging the capacitor, we're getting a little more into like non-linear functionality. You can see that there's a little bit of a kink in the charge-discharge curves here instead of them being a nice straight angle. But nevertheless, it is still working. So I'm going to just crank that down a little bit further and see if it will. So I'm going to put it down to about 0.25 hertz, so every 4 seconds or something. And then I'm going to try and reduce the input amplitude even further. Okay, so there's captured waveform. You can see we're still integrating from rail to rail quite happily. So I'm going to change the amplitude now down and see if it still is able to keep up. I've gone down to 50 millivolts of input. So let's just see what happens here. Got to wait for the scope to come back to us. So both of these are open. Now it looks like the voltage one, which has the 100K on the input, is actually no longer ramping right down to the negative rail. The current one definitely is, but the voltage one, I think, probably because of that 100K on the input, is now limiting itself. So I think what I'm going to probably do here, just so that we don't ever lose the low end resolution of trying to compensate for voltages, I'm going to throw the 22K back in there again. And see if that actually fixes that, and I'll probably just go with that with different values of capacitors. Alright, so that's it in right now, and it looks like it did fix it. The noise is probably just from me playing around with it. Yeah, they've actually affected each other slightly. I'm not sure why. It looks like they're drifting around a little bit. It might be because of noise and things on the on the board, but that certainly made them work a little bit better. If I just increase the amplitude of the input, I've gone to 70 instead of 50. And you can see that at that point it's immediately started working again properly. The integration time, of course, is very, very long right now. We're at almost, I just move my arm out of the way and try to adjust this without blocking it. All right, where the voltage one is at 400 milliseconds now, so it's almost a half a second to compensate for the voltage change. And the current one is about a quarter of that, so it's about 200 milliseconds, which if you consider that the input is only changing by 70 millivolts peak to peak. So if I do the math on that, 70 millivolts, that's instead of 7, so it's a tenth. It's 1% of the input is all that's changing. 1% of the output voltage on the input is changing, and this is still able to adjust itself within a half a second of that. Now if you wanted it to respond faster than that, of course you change your capacitor resistor values. But I think that for that kind of offset, the current one is responding quicker, because that's, often it's more problematic if you exceed currents and things. The voltage one, it's responding still very, very well. So I think that that pretty much will complete the experimentation there. I'm starting to repeat myself a little bit. I hope you find it interesting. If you like it, give it a thumbs up or a like, depending on where you're watching this from. And I hope you've learned something. I certainly have over these last two videos. Now we've looked at the differential voltage and current selection to monitor the output of the power supply, and we've looked at using an integrator to control the MOSFETs. So if you remember from our circuits, if I just bring it up here a second, let me just go back to the drawings and we'll just go through something very quickly. Alright, so what we've got here is basically we've got a 22K on both sides of these right now, and we've got a 10 nanofarad and a 47 nanofarad still. So this is basically the same circuit. But if you remember from the control here, all right, now we're seeing that the output of this integrator, even with a small input of less than 1%, will still drive itself from rail to rail in order to compensate for not getting the right output voltage on the power supply or the output current that you want. When these things drive down to the negative rail, they're going to pull down on these V control or I control, and they're going to be turning this MOSFET off, which is pretty good. So I think the next stage we need to do is actually rewire my breadboard a little bit to try and clean it up, and actually hook in a MOSFET and actually build this last stage of the circuit and see it all working. Okay, so let's put the theory to practice. We've tested all the individual pieces, and they seem to work very, very well. So now let's do it. And that will be on a separate video. So I'm trying to keep all of these things as short as possible, although I think I'm still going quite a while. But anyway, let's pack this one up and go to the next one where we put everything together.